My title of my presentation is Conformational Dynamics Dictate Histone de-acetylase Activity and Inhibitor Binding. I'm working on this histone de-acetylase protein, which de-acetylates the lysine side chain of histone and some non-histone protein and regulate the expression of the various protein. There are total 11 HDAC protein, that is HDAC1 to HDAC11, which are divided into four classes, on the basis of their sequence similarity with the yeast protein RPD3, HDA1, and SIR2. In class 1, there are the four HDACs are present, that is HDAC 1, 2, 3, and 8, and which are linked to several diseases ranging from the cancer to neurodegenerative disorder. To date, total 4 HDAC inhibitors, varinostate, remidepsin, phenobnostate, and belnostate, have been approved by US FDA for the treatment of the cancer, but all these drugs are targeting more than one HDAC, and that's why they are associated with the adverse side effect, and as a result, now the focus of the inhibitor designing is shifted towards the specific isotype, and that's why we started working on the HDAC8. Why HDAC8? Because HDAC8 is different from the other class 1 HDAC. If you see HDAC 1, 2, 3, it has the C terminal, which has the regulatory serine residue. While in case of the HDAC8, regulatory serine is present in the catalytic domain at the 39 position. On the other hand, HDAC 1, 2, 3 is either show low activity or inactive in isolation, and they show very high activity when they express in the co-activator complex, while HDAC8 is very active in isolation. HDAC 1, 2, and 3 become active upon phosphorylation, while HDAC8 become inactive upon phosphorylation. Also, HDAC8 is having the prominent role in the specific cancer subtype, that is T-cell lymphoma and childhood neuroblastoma, and mutation leading to change in the activity of the HDAC8 was reported in the Cornelia de Lange syndrome patient. Therefore, we started working on this because it is quite different from the other class 1 HDAC. And when we started the project, what was known about HDAC8? The structure of the HDAC8 was known, but all the structure was known only in the bound form. And if we look at the structure of the HDAC8, it has the 8-stranded mixed beta seed surrounded by 11 helices, and it has 1 zinc ion and 1 potassium ion at the catalytic site and 1 potassium ion at the distal region from the catalytic site. And this secondary structure is connected by the 7 loop region, which is having at least one residue which is directly involved in the catalysis. And mechanism of the de-acetylation was also known on the basis of the Kisher structure and on the basis of the site-directed mutagenesis biochemical activity. And in the Kisher structure, people have observed the two cavity, one cavity that is known as the binding tunnel, where the substrate used to bind, and another cavity that people have observed adjacent to the binding tunnel, which people have proposed to involve in the release of the product acetate after the de-acetylation. What was our aim? Our aim was the elucidation of mechanism of the regulation of the HDAC8, which already we have achieved, where we have identified a regulatory region in the HDAC8. And the second aim was understanding the role of functional loop in the product release, and that was already achieved by the molecular dynamics simulation. And currently I'm working on the investigation of the structure and dynamics of the HDAC8 in the free as well as in the bound state, and understanding the role of the functional loop in the different steps of the catalysis. And for that, first thing what I did the structure-based assignment of the ILVM spectrum of the HDAC8. This is the methyl TOG spectrum of the HDAC8, where the peak correspond to isoleucine C delta 1, valine C gamma 1, C gamma 2, leucine C delta 1, C delta 2, and methionine C epsilon. And these residues cover 25% of the primary amino acid sequence, but you can see it actually covers the whole tertiary structure. And these residues are very close to the residues which are important, which are very known for the basis of the biochemical activity. And After that, first thing after the assignment, first thing I did, the interaction of this inhibitor, that is trichostatin A, which is actually a competitive inhibitor, And when I did the binding of this inhibitor, I found the residue, some residue from the active site is showing the chemical shift perturbation. Along with that, some residue which is actually far away from active site is also showing the chemical shift perturbation. And when I fitted the data all together, I found the KD value is 5 micromolar with a off rate of 0.01 per second. And it shows that this complex is very stable. Complex is very highly stable and will be very homogeneous to do the NMR. And that's why I did all the experiment in the free state as well as in the bound state with the trichostatin A, because I have used this one as a substrate. And for that, first thing I did, I did the CPMG-based relaxation dispersion experiment to identify the invisible state in this HDAC8 protein. And for introduction, if we see this kind of the decay curve in the relaxation dispersion experiment, it means that residue is having at least one excited state. And the difference between the R2 effective value with low CPMG and at the high CPMG, at you can say infinity CPMG, is known as the REX value. And we fit the data we used to get the two global parameters, that is the population of the ground state and the population of the excited state. And we get the exchange rate between the ground state and the excited state. And along with that, we used to get the residue specific parameter, that is the delta omega, that represent the chemical shift difference between the ground state and the excited state. And then I recorded this experiment for the HDAC8, and I found the residue from these four regions, L1, L2, L6, and the catalytic region are showing the dispersion. This is in the free state. This is in the TSA bound state, that is, you can see in the bound state, residue showing the dispersion. Now, why I said this one as a catalytic region? Because it has this histidine 142 and 143, which directly involve in the hydrolysis step. And now the question arises, can I fit this data together? And for that, they have to be they have to show that the similar process. But when I look at the data, I found this catalytic region is entirely in the different process than the L1, L2, and L6 region. And also, when I added the TSA, that trichostatin A inhibitor, I found this L1, L2, L6 region, REX value increases, while the catalytic region, the REX value got decreased. So definitely I have to fit this catalytic region separately from this L1, L2, and L6 region. Now, can I fit L1, L2, L6 region together? Then I saw the data. I found that in presence of the TSA, with the decrease in temperature, the REX value decreases for the L1 region, while with the decrease in the temperature, REX value increases for the L2, L6 region. Therefore, I need to perform three fittings separately, that is the catalytic region, L1, and L2, L6 region. And I performed three different fittings, as you can see on this figure. This catalytic region is best fitted in the two-state model, that is the ground state to excited state. It means this region is just having the one excited state, while this L1 and L2 L6 region is best fitted in the three-state model. In the free HDAC8, the data is best fitted in the bifocal model, that is E1 to G to E2, while in the inhibitor bound state, the data is best fitted in the linear model, that is G E1 to E2 state. After the when I fit the data, I got the population of the ground state and the population of the excited state in the free HDAC8 as well as in the inhibitor bound state. Now the question arises, okay, what are these excited state? And for that, I found the change in the delta omega between the ground to the excited state 1 is showing the linear correlation with the change in the chemical shift observed in the methyl TOG spectrum upon the inhibitor binding. It means the first excited state observed in the free state is nothing but the bound state, while the first excited state observed in the TSA bound state is nothing but the free state. Now the question is, what is the second excited state? For that, I found that the delta omega for the second excited state is showing the linear correlationship with the change in the chemical state upon this DCPI inhibitor binding. This DCPI inhibitor is the H-decade specific inhibitor which open the acetate release channel in the L1 region. It means this second excited state is nothing but the release state. Therefore, we can say this in this L1 and L2, L6 region, in the free in the free and in the bound for this L1, L2, L6 region is sampling between free, bound, and release state conformation. Now the second, what is the excited state in the catalytic region? After the fitting the data, I found in the free H-decade, I found the population of the ground state is approximately 93%, while in the inhibitor bound state, the ground state population is 98%. It means this inhibitor is just stabilizing the ground state. And in my chemical shift methyl-2G spectrum upon TSA binding, I found this L1, L2, and L6 region are showing the change in chemical shift, while this catalytic region is showing no change in the chemical shift. It means this region is always in the bound state. Also, I found a linear correlation between the delta omega of the free and the delta omega in the inhibitor bound state, which shows that this region is sampling the similar excited state. And in my previous molecular dynamic simulation, I found this histidine 143 of this region is sampling between the two states. That is, one is the crystal structure state, that is the more in the bound conformation, another state which is more open, and that I defined as the release state. And on the basis of this comparison, I can say that this catalytic region is just sampling between the bound and release state. Now the question is, are these populations and all are really related to activity or not? And for that, I thought to create some mutation to alter the population of these excited state and to correlate that with the change in the binding and the change in the activity. And for that, I created the two mutations, that is L179-A and M2742A. Why these two mutations? Because I have observed NOE in my methyl NOE spectrum. And that's why I thought this will be good to alter the population of this L6 region. And when I recorded methyl-2G spectrum, I found this for both L179A and for M274A, the chemical shift is always away from bound and the free state. It means there is definitely a destabilization of the bound state. Now, to validate this, then I recorded the data of the CPMG at the 3 different temperatures in the similar way as the wild type H-decade, and I found a linear correlationship between the delta omega of the wild type H-decade and delta omega of the mutant H-decade for all the fittings. It means this mutant is also sampling the similar excited state as the wild type. But along with that, I found a big change in the population of my excited state 1 and excited state 2. I found a decrease in the population of the excited state 1, that is the bound state, while I found a increase in the population of my excited state 2. And when I did the titration of mutant H-decade with the TSA, then I found the increase in KD value from 5 to 105 micromolar, from 5 macromolar to 105 macromolar, that is 20 time increase. And similarly, I found a change in activity from 100 to 5%. And it means this change in activity is well correlated with the change in KD value. It means this activity change is basically reflecting the change in Km, and this change in the binding affinity is very well correlated with the observed change in the population of this bound state. Similar thing then I did for the M274M mutation, where also I found linear correlationship between the delta omega for the wild type H-decade and for the mutant H-decade. It means again this mutation is sampling the similar excited state, but here in this case I found only change in the delta, only change in the population of the excited state 1, almost there is no change in population of the excited 2. But when I did the titration study, I found a KD value from 5 to 113 micromolar and change in KD, change in activity from 100 to 3%. And again, the change in the KD value is very well correlated with the change in the population of the bound state. Now the question arises, can I make a dynamic mechanism by putting all the data together to illustrate a dynamic mechanism of the histone de-acetylase activity? And for that, first, assume the 5 species involved in the histone de-acetylase catalysis. That one is enzyme substrate complex, enzyme bound to product lysine and acetate, enzyme bound to product lysine, and enzyme bound to only with the acetate. The first assumption I have made, the enzyme and enzyme bound to product acetate will have the similar kind of dynamics because they have the free binding tunnel. While the enzyme bound to substrate, enzyme bound to product lysine, and the acetate and enzyme bound to product lysine will show the similar dynamics because they have the something which is binded already to the binding tunnel. It means active site is not free. And also I can connect these with the just with 3 parameters, that is K on and K off rate and the rate of hydrolysis that is already known from the biochemical experiment. And then within each species, I can have the 18 conformation, 3 for L1, 3 for L2, L6, and 2 for the catalytic region. And then I assume this hydrolysis is going to happen only from the conformation where the L1 is in bound conformation, L2, L6 is in bound conformation, and the catalytic region is in the A state, which is actually the state which is observed in the crystal structure. And this region only we have assumed where this L1 region will be in the release state, that as we have observed in our CPMG experiment. And then we've put our K on, K off value, our Kcat over Km value on this fitting. And here you can assume there are total 93 states, 18 in each, and one is substrate, one is the product acetate, and one is the product lysine. Total 93 states. And then I want to find out, okay, where the substrate binding and dissociation will happen and where the product lysine product dissociation will happen. And for that, when I perform a least square fit, I found the reduced minimum chi-square value for this, where the L2, L6 region either in the free state, either in the release state. It means this lysine product dissociation and the substrate binding and dissociation is going to happen only from these 2 places. And then to validate this, what I did, just I replaced the data of the wild type with the data of the M274A. And then I found the value of KD, K off, and Kcat over Km, which is very well correlated with the observed experimental value. It means the CPMG experiment is enough to explain all the enzymatic parameters, Overall, what I concluded, I found the millisecond dynamics in the 3 regions of the protein, that is L1, L2, L6 region and catalytic region. L1 and L2, L6 region is in sampling between apo, bound, and release state, while this catalytic region is sampling between bound and release state. And we have identified the predominant role of L2, L6 region in substrate and inhibitor binding, L1 region in the release of acetate, and catalytic region in the hydrolysis. And we found that dynamic sampling of different conformation of histone de-acetylase enzyme actually dictate the enzymatic activity and the inhibitor binding. At the end, I want to acknowledge Professor D. Fleming Hansen, my postdoc supervisor, and my lab mate. Special thanks to Lucas and Nico, who worked with me on this project.